Hello students. Today we are going to consider the chapter on force, work, power and energy. What exactly is force? Why is it that we need force in our day-to-day life? How does force play a vital role in our day-to-day life? Let's consider what we had studied in 9th standard as regards force. We considered mass of an object. The mass of the object is nothing but the matter contained in a body. We know that mass of a body remains constant all throughout the surface of the earth. Whether we go on the poles or we go on the equator, the mass does not change purely because it is the matter contained in a body. However, we also considered what is weight. Weight is nothing but the gravitational force that is acting on a particular mass towards the center of earth. This weight definitely changes as we go around the equator as well as at the poles. That is because acceleration due to gravity varies at the poles and the equator. The SI unit of mass is kg and that for weight is Newton. We also studied what is inertia of a substance. Inertia is nothing but the matter content of a body. We have two types of inertia, that is inertia of rest and inertia of motion. When inertia of rest is considered, we say that it is the tendency of a body to remain in its state of rest unless and until an external unbalanced force acts on it. Similarly, inertia of motion. When a body is set into motion, definitely it would continue its state of motion so long as no external unbalanced force acts on it. With these basics of 9th standard, we proceed to our major chapter, that is force, work, power and energy. We say force as that physical quantity which, when applied on a body, changes or tends to change the state of rest or of uniform motion. We know that force, when applied on a body, is used to write, to read, to swim, to snore, to eat, to walk, and so on. In short, on a day-to-day basis, we do require force for our day-to-day activities. However, we see that when force is applied on a body, it changes its state of rest. Say for example, in case of a snooker game, when the stick hits the ball, we see that when the force is applied by the stick on the ball tends to move forward. That means a force is applied by the snooker stick on the ball that is at rest, thereby making it in motion. We have force that changes the state of motion also. All of you must have seen go-karting. In go-karting, we know that when the driver applies the brakes, this particular car definitely comes to a halt. That is because braking force is applied by the driver to the car that is in motion. We have the change of shape also. In that case, we see that when a lemon squeezer is used to squeeze a lemon, to extract the juice from it, definitely force is applied on the lemon squeezer. And when the force or effort is applied on the lemon squeezer, the shape of the lemon changes. So force definitely causes change in shape. We also have change in physical state. All of you must be knowing about the Gola candy. The ice is being crushed initially, and later on we see that as these lumps of ice are pressed together with the force, they reunite together or refreeze together. So we have such day-to-day examples as far as the force is concerned. Talking about force, force is that physical quantity which, when acts on a body, changes or tends to change the state of rest or of uniform motion of a body along a straight line. Its SI unit is Newton and CGS unit is dyne. The correlation between CGS and SI unit of force is 1 Newton is equal to 10 to the power 5 dyne. we definitely can obtain this relation by using Newton's second law of motion. Talking about Newton's second law of motion, we definitely have certain terms that are used in it. Like, for example, momentum. When we talk about momentum, it is nothing but the quantity of motion possessed by a body due to the collective effect of mass and velocity. Say, for example, I have a striker that is striking a pebble on the carom board. When the striker applies a force on the pebble, definitely we see that the pebble is set into motion. So the quantum of motion that was possessed by the striker is transferred to the pebble. As a result, the pebble starts moving. So we say that the motion has been transferred or the momentum has been transferred. Looking at this, we can define momentum as, momentum is nothing but the quantity of motion possessed by a body due to the collective effect of mass and velocity is called as momentum. Mathematically, linear momentum is equal to mass into linear velocity. Its SI unit is kg meter per second. Along with momentum, we also think about impulse. What exactly is impulse, or where does the concept of impulse hold true? All of you must have seen that a carpenter strikes a hammer on the nail while fitting two wood objects together. What is he doing? He is implying an impulsive force. So when a hammer, that is when a very large force, acts on a body for a short interval of time, the collective effect of force and time is called impulse. Mathematically, impulse is equal to force multiplied by time. SI unit is Newton second. With these two basic fundamental quantities, we go on to the statement of Newton's second law. How do we say the Newton's second law? The rate of change of momentum is directly proportional to the impressed force and takes place in the direction of force applied. The rate of change of momentum is directly proportional to the impressed force and takes place in the direction of force applied. Mathematically, force is equal to mass into acceleration. Okay, so talking about Newton's second law of motion, as we stated, force is equal to mass into acceleration. We also had said about the SI and CGS unit of force. 1 Newton is equal to 10 to the power 5 dyne. How do we obtain this? Going back to your Newton's second law of motion, force is equal to mass into acceleration. If I take the SI unit of individual quantities, 1 Newton is equal to 1 kg into 1 meter per second square. 1 kg to be obtained in grams is 1000 grams. 1 meter per second square is 100 centimeter per second square. Expressing in 10 to the power factor, it works out to be 10 to the power 3 gram into 10 to the power 2 centimeter per second square. That is 10 to the power 5 gram centimeter per second square. The CGS unit of force is dyne. 1 dyne is equal to 1 gram into 1 centimeter per second square. So I can replace gram centimeter per second square by a dyne. Therefore, 1 Newton is equal to 10 to the power 5 dyne. Then we go on to the concept of conservation of momentum. When we talk of conservation of momentum, definitely we are talking about the motion of the body that is possessed on striking two objects. Let's consider two marbles in this case. When one marble strikes another marble, we see that the quantity of motion that is possessed by one set of motion is transferred from one system to another. And when it is transferred from one system to the other, we say that the momentum before impact is equal to total momentum after impact. Giving you the statement of this. When two bodies collide with each other elastically, remember it should be an elastic collision. When two bodies collide with each other elastically, the total momentum before impact is equal to total momentum after impact. Mathematically, m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. So whatever quantity of motion was possessed before the motion is same as the quantity of motion after the motion. The next concept that we go across is the concept of work. When we talk about work, we always feel that I have been doing work so long and I get tired because of doing work. Why is it that this fatigueness or this tiredness is coming in a person? It's because the person is doing work. So what do we understand by doing work? Work is said to be done when a body is displaced in the direction of force applied. So if I am displaced from one position to another position, we can definitely consider work to be done. However, it's not necessary that it is along a horizontal plane. Maybe a person is climbing up a hill or moving around a spiral staircase. Definitely we say that in either of these cases also, work is done. So in general, we can define work as work is said to be done when a force or a component of force displaces the body in the direction of applied force. Mathematically, work done is equal to force into displacement, or work done is equal to F cos theta multiplied by S. You must have studied basics of trigonometry in your 9th. However, just to help you out over here, what exactly is this F cos theta? We have a force that is acting along an incline, that is at an inclination of theta with the horizontal. If I resolve this force into two components, one perpendicular and the other horizontal, then the vertical component is F sin theta and the horizontal component is F cos theta. It is this F cos theta that is responsible for its work done. So we have a general relation as work done is equal to force into cos theta multiplied by displacement. SI unit of work is joule and CGS unit of work is erg. Talking about the correlation between work, CGS unit and SI unit. 1 joule is equal to 10 to the power 7 ergs. We obtain this relation by using the formula work done is equal to force multiplied by displacement. In SI unit, 1 joule is equal to 10 to the power 5 dyne multiplied by 10 to the power 2 centimeter. Since the powers are same, therefore we add the indices wherein we get 10 to the power 5 multiplied by 10 to the power 2, that is 10 to the power 7 dyne centimeter. 1 dyne centimeter is nothing but 1 erg. So if we substitute this, we get 1 joule is equal to 10 to the power 7 erg. Talking about the concept of 3 categories of work. Work can be broadly classified into 3 classes: positive work, negative work, and zero work. Talking about positive work, when the body is displaced in the direction of force applied, we say positive work is done. Second case, negative work. when the body is displaced against the direction of force applied, we say negative work is done. Could we give an example of positive work? When we are walking along a horizontal path on a road, we say that positive work is done. Similarly, for negative work, if I am swimming across water level, then I see that the water offers certain resistive force, which can definitely be considered as negative work. I am moving in the forward direction, the water is offering a resistive force. So negative work is done. Concept of zero work, a very interesting concept. Taking you back to the relation of force multiplied by displacement is equal to work done. We get work done can be zero provided force is zero, cos theta is zero, and displacement is zero. Out of which we eradicate the part force equal to zero. So we are left out with two components. One is cos theta equal to zero, and second, displacement equal to zero. So when I say that the net displacement of the body is zero, we can conclude that work done is zero. Can we have few examples for it? Sure. Say for example, a person is running a running race. The start point and the finish point is the same. So definitely the net displacement of the body is zero. Since the net displacement is zero, we can say work done is zero. Another example, supposing you have a porter who is standing on the platform with the luggage on his head. Definitely here also the work done is zero. Why? Because there is no net displacement of the porter. As a result, we can say that work done is zero. The second component which accounts for zero work is cos theta equal to zero. This cos theta equal to zero comes when theta is equal to 90. We know that theta is nothing but the angle between the force and the displacement. So when the force acting on the body is perpendicular to the displacement, we say that work done is zero. Can we have another example for this part of it? Well, we can consider again an electron that is revolving around the nucleus. When an electron is revolving around the nucleus, at every point on its periphery, we see that there is a centripetal force that acts towards the center, towards the nucleus. And at the same point, we have the displacement that is tangential to the centripetal force. So at every point on the path of an electron moving around the nucleus, we can definitely say work done is zero. I hope concept of positive work, negative work and zero work is clear with you.